Hello students, welcome to the fourth video lecture of electrostats. So let's proceed in chapter number 1, electric charges and fields. So we were about to start electric lines of force due to a point charge. In this video lecture we started electric field lines or electric lines of force in the last video lecture. So let's proceed. Let's have a point charge, that is q is greater than 0, so electric lines of force will be radially outward like this. Q greater than 0 means positive charge. If point charge q is less than 0, negative charge, so the electric field lines will be radially inward. Radially inward means if we join equidistant points on the electric field lines, so we'll get a sphere. So the electric field lines will be along the radius of the sphere. So that's why the word radially inward or radially outward is used. Representation of electric field in terms of field vectors we have done over here. The size of the arrow represents the strength of the electric field. You can see the size of arrow is decreasing as we move far away from the charge. So it shows that electric field strength decreasing. And near the charge, near the positive charge or near the negative charge, you can see the electric field line. The size of arrow is what? Large, so electric field strength is what? High. You can see if we draw the line continuously, so we'll get the pattern like this for q is less than 0 or q is greater than 0. Representation of electric field in terms of field lines. Next, electric lines of force due to a pair of equal and unlike charges or dipole. If equal and opposite charges are placed at a very short distance, so that combination is called as dipole. So we are going to have the electric lines of force pattern due to the dipole. So this will be the pattern of electric field lines or electric lines of force due to a dipole. Point P if we choose, and if you want to find the direction of electric field line at point P, so it will be obtained by drawing the tangent at that point P. You can see if point P, again I am repeating, if at point P we have to find the direction of electric field, so thus just draw the tangent at point P, we will get the direction of electric field. You can see this pattern which is covered in this dotted box. Electric lines of force contract lengthwise to represent attraction between the two unlike charges. So lengthwise contraction is there to represent the attraction. Next, electric lines of force due to a pair of equal and like charges. If the charges are same, it means both are positive or both are negative. So the pattern we are going to draw. So you can see these two charges are positive charges. You can see this is the pattern of electric field lines. So if you place a test charge anywhere around this, so the test charge movement will always be along the electric field line. Test charge is always positive in nature. It is assumed to be positive in nature. Being very small, it does not disturb the electric field of the source charge. These informations we already have about the test charge. So you can see the repulsion. Due to the repulsion, the electric field lines pattern is like this. In this region you can see there is no electric field, so that's why electric field lines are not lying in this region, so that's why this is called as neutral region. And this is the pattern. Electric lines of force exert lateral sideways pressure to represent repulsion between two like charges. So you can see sidewise lateral pressure according to the pattern, and this is the pattern of electric field lines. Next, electric lines of force due to a uniform field. If field is uniform, field is constant at every point, like this. If one plate is positively charged, another plate is negatively charged, between the plates the field will be uniform, then electric field lines will be equidistant with each other. Let's understand the properties of electric lines of force or field lines. Number one, electric lines of force are imaginary lines. They are always imaginary lines. They are drawn actually by tracing the moment of test charge which is placed around a source charge. Second, a unit positive charge placed in the electric field tends to follow a path along the field line if it is free to do so. As I have told just now, if it traces the moment of unit positive charge, or we can say if it traces the moment of test charge, we get the pattern of electric field line. This way you can see. Again I show you, see on the diagram, this tracing the moment of test charge will get the pattern of electric field line. Next, electric lines of force emanate from a positive charge and terminate on a negative charge. So electric field lines do not form closed loop. They emanate from positive charge and terminate on negative charge, as you could see in the previous slide. And here also you can see. See this pattern on the diagram. The electric field lines emanate from positive charge and terminate on negative charge. Next property, the tangent to an electric field line at any point gives the direction of the electric field at that point. We just did the same thing on the previous slide. At any point P, we chose a point P over there and we drew the tangent and we found the direction of electric field at that point. Next property, and you can see in this diagram also, if this point P, at this point P, if you want to find out the direction of electric field, then draw the tangent at this point P. This will be the direction of electric field. Fifth property, the two electric field lines or two electric lines of force can never cross each other. If they do so, then at the point of intersection there will be two tangents. It means there are two values of electric field at that point, which is not possible. So finally we can say electric field lines cannot intersect each other. If they intersect, then at one point there will be two directions of electric field or two values of electric field, which is not possible. Further, electric field being a vector quantity, there can be only one resultant field at a given point, represented by one tangent at the given point for the given line of force. So at one point there will be only one direction, two directions is not possible. You can see, if like this kind of situation is there, then this situation is not possible at all. At this single point there are two directions of electric field. It means if we place a test charge over here at intersection point, the test charge would move in two directions, which is not possible. That's why this case is also not possible. Only one direction is possible. Next, sixth property, electric lines of force are closer, or we can say crowded, where the electric field is stronger, and the lines spread out where the electric field is weaker. If electric field lines are closer to each other, then they represent the strong electric field. If electric field lines are rarer, or we can say away from each other, it means it shows the weak electric field. You can see over here in this figure, if closer, strong electric field, and if they are spread out, weak electric field. And you can see if here closer electric field lines, it means this charge is having high magnitude because of strong electric field, and Q is having low magnitude because of weak electric field. Electric lines of force are perpendicular to the surface of a positively or negatively charged body. So either positive or negative charged body, the electric field lines will always be perpendicular to the surface. You can see over here, on the surface the electric field lines are perpendicular. Here also you can see the curved surface is there, but at any point on the surface, if we draw the tangent, the electric field line will always be perpendicular to the surface. You can see this perpendicular, always perpendicular. On the curved surface, if you want to check the perpendicular, draw the tangent at that point, then the electric field line will be perpendicular to that tangent. Next, electric lines of force contract lengthwise to represent attraction between two unlike charges, as we have seen in the previous slides. Ninth, electric lines of force exert lateral sideways pressure to represent repulsion between two like charges. This also we have seen in the previous diagrams. Next, 10th property, the number of lines per unit cross-sectional area perpendicular to the field lines, or density of lines of force or density of electric field lines, is directly proportional to the magnitude of intensity of electric field in that region. As much strong electric field intensity, that much dense electric field lines. As much low electric field or weak electric field intensity, that much far, or we can say that much rare electric field lines will get. So delta n by delta A, number of electric field lines per unit area, is directly proportional to electric field intensity or electric field strength. Next, 11th property, electric lines of force do not pass through a conductor. So electric field lines cannot intersect a conductor, they cannot enter inside a conductor. Hence the interior of the conductor is free from the influence of electric field. This property will elaborate in chapter number 2. Only you just read it out and keep it in your mind. If this is the electric field lines source, we can say over here, see there is a positive plate and on the right side negative plate. Electric field lines will be there from positive to negative plate, but they will not enter inside a conductor. No field inside. See, it is found outside, but they are not found inside the conductor. This phenomena is also called as electrostatic shielding. As I told, we will elaborate it in chapter number 2 also. Why it is why it is called as electrostatic shielding? Because the interior of a conductor is free from electric field, or we can say it is protected from electric field. That's why it is called as electrostatic shielding. Next property, 12th one, electric lines of force can pass through an insulator. If insulator is there, then of course electric lines of force can pass through the insulator. Next topic, electric dipole. I introduced electric dipole just now in the previous slides when I was teaching you the electric field lines. Again, let us understand separately what is electric dipole. Electric dipole is a pair of equal and opposite charges separated by a very small distance. If equal and opposite charges are separated with a very small distance, that combination, that arrangement is called as electric dipole. Electric field produced by a dipole is known as dipole field. Electric dipole moment is a vector quantity used to measure the strength of an electric dipole. So whatever be the strength of dipole, it is measured by the dipole moment, and dipole moment represented by small p, which is a vector quantity. Let's observe with the diagram, a negative charge, a positive charge, separated with a very small distance. This arrangement, as you can see, this 2L is a very small distance, and this arrangement is called as a dipole. Dipole moment direction, you can see vector P is the dipole moment whose direction is from negative to positive charge. You have to remember. The formula of dipole moment is P is equal to Q into 2L. Vector P is equal to Q into 2L into I cap, where I cap is the direction from negative to, is having the direction from negative to positive charge, and P is also having the same direction. That's why we have written vector P is equal to Q into 2L I cap. So the formula tells us that the dipole moment is the product of the magnitude of either of the charge and the distance between the charges. Magnitude of the charge is Q and distance between the charges is 2L. So same thing is written over here. The magnitude of electric dipole moment is the product of magnitude of either charge and the distance between the two charges. The direction is from negative to positive, we have discussed just now. The SI unit of P is coulomb meter, as you can see. Unit of charge is coulomb, unit of 2L is meter, so coulomb meter. Note point: an ideal dipole is the dipole in which the charge becomes larger and larger and the separation becomes smaller and smaller. It means as much smaller is the separation between the charges and larger with the magnitude of the charges, that much good dipole it will be. So that is called as ideal dipole. Now, electric field intensity due to a dipole. This is the next heading. It means we are going to study that if a dipole is there, then how to calculate the electric field intensity due to that dipole. So first case, we are going to observe at a point on the axial line. So let's see the diagram. There is a charge minus Q plus Q, vector P direction minus Q to plus Q, point A and B. These 2 points are there where charges are placed, and this is a dipole. The midpoint of dipole is O. Length is 2L, so half of the length of dipole is L. So O to A and O to B distance are L and L. We have represented over here in the diagram. So this line, the line which is extended along this AB, that is called as axial line, and AB is the axis of dipole. So on this axial line only we are going to calculate the electric field intensity. So we have chosen a point P which is lying on the axial line, and this point P is situated at distance x from the midpoint of the dipole, you can see. Now electric field due to charge at A means negative charge will be in inward direction. You can see EA towards left, EB towards right. Because of the positive charge, the repulsion will be there on the test charge, or we can say due to the positive charge the electric field lines are normally outward or radially outward, so that's why EB is towards left and EA is towards right, radially inward and radially outward. Net electric field EP will be equal to EB minus EA, as these two vectors are equal and opposite. So resultant electric field intensity at the point P is vector EP is equal to vector EA plus vector EB. Vectors EA and EB are collinear and opposite. Therefore, vector EP is equal to mod of vector EP is equal to mod of vector EB minus mod of vector EA. Magnitude form. Vector EA we can write 1 upon 4 pi epsilon naught Q upon x plus L whole square I cap, and vector EB is equal to 1 upon 4 pi epsilon naught Q upon x minus L square I cap. Here the negative sign will be there. Why? Because vector EA is acting with vector EA there will be negative sign, in the expression of vector EA there will be negative sign. Okay, why? Because EA is acting opposite to the direction of positive x-axis and EB is along the positive x-axis direction. So that is missed out from here, and we'll use directly in the formula. So vector EP, if we use these two values along with the negative sign with EA, or we can say in the previous expression where we have written in the magnitude form. Magnitude form if we are using, so directly we can use that negative sign over here. So we can write mod of vector EP is equal to 1 upon 4 pi epsilon naught q upon x minus L whole square minus q upon x plus L whole square. Let's see how it is. Vector EA is what? 1 upon 4 pi epsilon naught q upon bracket x plus L whole square. You can see EA is the electric field intensity due to charge at A. So distance of A to P is x plus L. A to P is x plus L, you can see, and distance from B to P is x minus L, and the charges are Q and Q only. Magnitude of the charges are Q only, so we have written like this: Q upon x plus L square for vector EA and Q upon x minus L whole square for vector EB. Other expressions, other things are already there, 1 upon 4 pi epsilon naught and I cap. So let's find out the resultant. So after solving it, we'll get mod of vector EP is equal to 1 upon 4 pi epsilon naught 2ql x upon bracket x square minus L square whole square. Further, if we solve, we get mod of vector EP is equal to 1 upon 4 pi epsilon naught 2px upon bracket x square minus L square whole square. Why? Because Q into 2L is P, that is dipole moment. We have already defined it on the in the previous slide. So at the place of Q into 2L we have written P, so we have got the expression like this. In the vector form we can write like this: vector P is equal to 1 upon 4 pi epsilon naught 2px upon bracket x square minus L square whole square I cap. Why? Because the resultant electric field intensity is acting towards right only, because EB is greater than EA, so resultant vector will also be acting in the direction of EB, and that is the positive direction of x-axis. That's why here I cap is used. If L is much less than x, and that is there, why? Because the dipole length is very small, the distance between the charges is very small. The distance between the equal and opposite charges is called as dipole length, and dipole length is very small. Half of length will be much small, so L is much less than x. So we will neglect L over here, and we can get the expression like this. Neglect L from the above expression, we can get the expression of EP as 2p upon 4 pi epsilon naught x cube. And this is the formula for electric field intensity due to dipole on its axial line. The direction of electric field intensity at a point on the axial line due to a dipole is always along the direction of the dipole moment. So whatever be the dipole moment direction, same will be the direction of electric field lines. Sorry, electric field intensity of the dipole on the axial line. So finally we have got the expression for electric field intensity due to a dipole on its axial line, in the vector form also, in the magnitude form also. Our next topic will be the electric field intensity due to a dipole on its equatorial line, but that will continue in the next video lecture. So you are supposed to revise this derivation and the previous concepts that we have studied in this video lecture. So we'll again interact again in the next video lecture. Till that time, keep working hard. Thank you everyone. Thank you for paying attention.